started here in a second. So if everybody could find your seats, I'm sure we'll start filling in here as the day goes on. We'll start this morning's program with our first set of speakers. After our first speakers, we're gonna break for lunch. Lunch is on your own. We've got an hour and a half, so it's plenty of time for you to explore some of the places on campus to eat. I believe we have a slide for the people here in the room for options to explore for lunch, if you're not familiar with campus. And then we're coming back at 1:30 this afternoon for our next round of speakers, and then coffee break upstairs in our beautiful Bender room, and then our awesome Peter Bellerby keynote this evening. So we've got a really nice day lined up for you. I'm going to hand the mic over to Jen Frazier, who is from our steering committee, to introduce our speakers. Thanks.
All right. Good late morning, everyone. It's nice to see everyone and to finally be in this space. I've lived in the Bay Area, but I've never been fortunate enough to be here. As Evan said, my name's Jen Frazier. I'm on the steering committee for this event. And I'm also a program officer at a local foundation called the Gordon and Betty Moore Foundation in the science program. So we have not funded or have nothing to do with this event, but the foundation and my own interests have long been in how can we use different kinds of visualizations, including maps, to help people better understand their world, especially through the lens of science. So it's been really fun to be involved in a different type of event. And this morning we have two great speakers. First, we're going to be sort of two different realms of time and space. We're going to have two 25-minute talks followed by 5 minutes of questions. And first up will be Dr. Luca Scholz on mapping anthropogenic weather, followed by mapping the subsurface processes of ice sheets and icy moons with ice-penetrating radar. Wow. With Dr. Dusty Schroeder. So first, please join me in welcoming, well, in a second, we only have one mic, so he has to wait just a moment. Dr. Luca Scholz, he's a senior lecturer and associate professor in digital humanities and history at the University of Manchester. His work combines archival research and computational methods to study the history of weather, information law, and freedom of movement in early and late modern Europe. His digital work develops new geospatial and data-driven methods to analyze and question data in historical and humanistic inquiry. Luca's first book, Borders and Freedom of Movement in the Holy Roman Empire, was published by Oxford University Press in 2020, and other writing has appeared in Past and Present, the Historical Journal, Cartographica, and Quaderni Storici. I hope I got that right. He earned a PhD in history at the European University Institute in Florence and subsequently held a Mellon postdoctoral fellowship at Stanford University. Please join me in welcoming Dr. Luca Scholz.
Thank you. Thanks so much for the introduction. Thanks to Evan and the team here at the Rumsey Map Center for organizing this wonderful event, and thanks to Barry Ruderman and David Rumsey for making it possible. Maps of the Earth's atmosphere rarely make interactions between humans and the atmospheric environment explicit. One genre of maps that foregrounds the links between human and atmospheric environments is that of anthropogenic weather, that is, weather induced by human activity. So I will discuss maps today that were produced in one of the most extensive projects of weather modification in European history, and that is the project of weather shooting. This was consisted in the firing of empty mortars, cannons, or rifles at storm clouds in order to avert hail, which was particularly common, but not exclusively, in and around the Alps. I'm completing a monograph on the history of weather shooting between the 18th and the early 20th century, covering German, Italian, and French-speaking regions, mostly around the Alps. And this project is also an attempt, a methodological attempt, if you like, to develop the digital historical study of atmospheric environment, and I'll share a couple of my maps. The focus today is not so much on that. Now, by the end of the 19th century, maps had become the key medium in which advocates and opponents of weather shooting advanced their arguments. And what's interesting here is that we're dealing with a production and a circulation of maps that happened outside of and sometimes in opposition to mainstream scientific institutions. So I'll proceed in 3 steps. I'll first quickly give you an overview of the history of weather shooting. I will then show you some of the maps produced by the weather shooters, and then I will show you some maps that were produced instead by academic meteorologists and scientists. So let's begin with weather shooting. The firearms employed for weather shooting range from handguns to mortars, such as the ones that you can see here, and in some cases even included rockets. A key reason why the storm cannonades, which are first documented in the early 1600s, but likely began even earlier, a key reason why these cannonades became controversial in the 18th century was the belief that storm clouds could be deflected away from cultivated lands into uncultivated plains or into mountainous, rocky, or forested or uncultivated land where they would cause less damage. The same belief led contemporaries to assume that storms had been shot towards them by their neighbors, engendering a flurry of disputes, as you can imagine. Now, this assumption that cannons deviated storms was not just limited to proponents of weather shooting, but was also widespread among officials and scholars. In fact, in Bavaria, it was the very notion of these extra area effects that eventually convinced the government to outlaw the practice. Now, this is perhaps best illustrated with a concrete example that I can show you, and this comes from the early 1770s in the borderlands between Bavaria and Salzburg. And the situation is the following. The subjects of several villages and towns belonging to the Prince Bishop of Salzburg petitioned their authorities to let them continue shooting at the weather after the practice had been outlawed a couple of years earlier. The petitioners, who lived in 2 villages, Holzhausen and Ringham, wrote that the storms usually moved from 2 nearby lakes in the direction of a mountain called Teisenberg, but that they were always repelled by the strong weather blessings performed by the clergy in Högelwörth, a monastery that you can see in the bottom right. At the bottom right. The farmers claimed that previously, when they were still allowed to operate their cannons, the cannons of Ringham, of Holzhausen, also of Saaldorf, had been able to either dispel the storm clouds or to direct them towards the mountains close to Teisendorf, where then the precipitation would fall into the forests. Now that they were prohibited from shooting, the storms resumed to threaten their lands. And the petitioners were successful. The Salzburgian subjects along the Bavarian border were eventually allowed to operate their cannons again, under the condition that they only pointed them towards Bavaria. Now, what's clear here is that the atmoterrestrial geography that is described by the petitioners was informed by beliefs and by structures that were specific to their cultural and political context. At the same time, we should not reduce the geography of these weather wars to cultural beliefs alone. If we consider the physical tracks of the storms described by the petitioners, well, these are consistent with the region's climatology and the westerly and southwesterly winds that are characteristics for most hailstorms in this area. So what you're seeing here is more recent radar data that a Swiss meteorologist was kind enough to share. So this is from a selection of storms from the 2010s, and these are the centroids of the storms. And you can see that to the petitioners, this irregular morphology of the storms resulted from the interplay of human and non-human forces. But the juxtaposition of I think that the juxtaposition of climatological data and archival narrative spotlights the extent to which the storms of the late 18th century were really socio-natural hybrids. Now, in the late 18th and 19th centuries, authorities repeatedly attempted to suppress this practice, but rural populations persisted to the point of staging violent revolts, and the storm cannons remained in use throughout the 19th century and experienced a revival at the turn of the 20th century. Now, I'm currently assembling data on the proliferation of the cannons in the 19th and the 20th centuries. I'm collaborating also with a research assistant in computer science to make this data interactively available. Aditya Mehrotra included his GitHub here. Was very excited about his work being showcased at Stanford, which for computer scientists holds a particular place in their heart. And we can also see that the distribution of the cannons, of course, follows the climatology of hail. That has to do with the orographic lift, so the precipitation that is produced when moist air is lifted as it moves over a mountain range. and which makes severe hail a particularly frequent occurrence in these very regions around the Alps. Now, there was much more continuity between the early modern forms that I showed you earlier and the the late 19th century forms that I'm discussing today. There was much more continuity between those than second wave storm artillerists care to admit. But there were also important changes both in the discourse and the material culture of this practice. One conspicuous shift were the new types of cannons that were used, new loading mechanisms, and as you can see here, ever larger cones. Now, it is out of the question that weather shooting, early modern or late modern, had any physical impacts on the weather. It did, however, engender a rich cartographic record, and that is what I want to discuss here. And let me begin by the maps produced by the weather shooters. In the late 19th and early 20th century, weather shooters regularly included maps in their reports and their correspondence with each other, but also with authorities. Many of these maps produced by the weather shooters strove to present their consortia, because they're organized in consortia, as coherent, self-contained, disciplined units. Lines were often drawn so as to connect each hail cannon to its nearest neighbors. In other maps, lines traced the perimeter of areas protected by the cannons, and the language accompanying these maps mirrored this sense of self-containment. So the letter in which I found this sketch, for example, describes the cannon network as a fully enclosed network here. There is also a conspicuous absence of topographical features, such as elevation and land cover, including distinctions between cultivated and uncultivated land, which you would think would matter in this context. This map that you're seeing here was included by a report of a hail cannon consortium in Conegliano in the north of Italy, does not consider elevation at all, despite this area being situated right at the foothills of the Alps. Indeed, many of these maps portray a distinctly geometric sensibility. In France, for example, hail defense associations were encouraged to determine the location of cannons using maps of their communes before setting them up on the terrain. Topographical or meteorological considerations were to play no role in what was envisaged as a strictly geometric exercise. Each cannon was thought to protect the area within a specific radius, and the cannons were to be arranged accordingly. And these maps, again, omitted any references to the natural world other than bodies of water. Storms themselves were usually represented as discrete, directed entities that followed predictable tracks. Now, this presumed regularity of storms was essential to establishing the effectiveness of weather shooting. And this was because the cannonades were considered successful if hail fell around a protected area, but not within it. Some even reported that wind, lightning, and thunder ceased within the protected area while they continued outside. This schematic map that you see here of a storm over Artignano in 1899 is a good example. The hail, the artillerist claimed, stopped sharply at the perimeter of the protected areas. But there was some hail that fell at the center of the defended area, and this was blamed on 6 stations whose shooters refused to shoot because they were hoping for rain. Here is another example from Styria in Austria, where several storms breached the area that should have been protected by the cannons. Now, of course, there are exceptions to these linear representations of storms. A notable one is the sketch produced in 1912 by a hail defense association in the Loire department. By this point, it was more common to use rockets. The sketch map represents a storm that had 3 cyclonic centers in which the crops were almost entirely destroyed. And rather than following a linear movement, the storms moved into all directions, as indicated by the arrows and the accompanying report. Now, collecting the data needed to create such maps was anything but straightforward. Differences in arrangement, equipment, and the operation between hail cannon consortia hampered efforts to harmonize the data collected by the artillerists. Observation booklets were distributed to artillerists to record the number of shots and the characteristics of storms. And in some cases, storm observation involved participatory mapping in which farmers became cartographers of sorts. And there were adverse incentives, which regularly led artillerists to exaggerate or embellish the effects of their shooting. In Styria, for example, unless the fall of hail was so severe that it could not be denied, they preferred not to report it so as not to be blamed for inadequate shooting. Shooters also exaggerated their success, claiming to have dissolved threatening storm clouds from which one could already hear the sound of hail. So this much about the maps that were produced by the weather shooters. Now let's compare this to the maps that were produced by meteorologists. As the cannons spread and governments developed more interest in this phenomenon, meteorologists and scientists also began to study the problem. And they also turned to maps to resolve the question. Now, if we compare their maps and those of the weather shooters, one of the most conspicuous differences concerns scale. Meteorologists tended to opt for much smaller scales. That means their maps covered larger areas. In this meteorological account of hail in the upper Po Valley, for example, the major storms of the season were represented in large maps at the scale of the region with synoptic scale inset that you can see at the top left. Synoptic pressure maps also feature prominently in another Italian report from 1902. And this was really a well-established genre by the time. Synoptic weather maps were widely adopted by meteorological agencies in the last third of the 19th century. So these were maps that visualized and still widely used atmospheric pressure, weather fronts, wind speed and direction, air temperature and weather conditions at specific locations at one point in time, which is why they are called synoptic. Now, what is remarkable here is the contrast between the scales at which academic scientists envisaged hailstorms and the scale that was preferred by weather shooters in their own maps. And you can see this contrast here. So I've mapped over the same expanse. So we're looking at the Western Alps. And you can see on the left a map that was produced by a consortium of weather shooters. You can see on the right a map that was produced by a physicist, a meteorologist charged with studying the phenomenon. Even stronger is the contrast here. So consider the contrast that we have between the weather shooters maps on the left and the meteorological maps that we have on the right. In fact, weather shooters occasionally complained that it was difficult to find maps of sufficiently large scale to use in their experiments. And there was an epistemic difference at play. Weather shooters insisted on describing the cannon's effect on individual storms. They mapped the storms at the scale of human experience. They recounted their battles one by one. And they remained beholden in many ways to the event narratives that were characteristic of the earlier meteoric tradition that was described by my colleague Vladimir Jankovic. Instead, the director of a French observatory emphasized the importance of studying storms, and I'm quoting him, in their relationship with the general situation of the atmosphere, rather than just observing storm clouds from the ground. And this also implied the use of daily synoptic weather charts. The smaller scales and the inclusion of meteorological data in these maps was a direct reflection of attempts by scientists and academics to reorient the discussion to, and I quote again a meteorologist, to be more in harmony with the nature of the phenomena to be investigated. And really what this reflects are wider debates in meteorology and climatology at the time about the most appropriate scales at which hailstorms were to be mapped and understood. The Swiss Meteorological Agency, for example, insisted that the formation of storms depended on the general weather situation and accordingly was to be mapped over large expanses. Others claimed that the local differences of hail required the consideration of topography, of hydrology and vegetation in much smaller spaces. And it's important to stress here that meteorological investigations of weather shooting were not stuck at the synoptic scale, but indeed combined different scales. While weather systems were mostly mapped at the synoptic scale, hail suppression efforts were regularly mapped by meteorologists at the scale of individual consortia. And this speaks to a wider sensibility in dynamic climatology at the time to integrate phenomena of radically different dimensions. So Deborah Cohen has famously written about this. But I also feel that in the documentation of weather shooting, the contrast between the scale of weather, the maps, the synoptic maps that we have just seen, and that of the cannons feels deliberate. Now, creating maps of the cannons and of the damages caused by storms was a time-consuming task. In a letter that I found, one physicist complained that the inspection and visualization of the damages caused by a single storm took him 8 days of work. Plans to expand existing storm observation networks staffed by volunteers succeeded only in part and failed to provide conclusive evidence for or against weather shooting. And the cartographic documentation left by meteorologists also betrayed the often disorganized reality of hail suppression, as in this map of a consortium on Lake Garda, in which an isolated dot, and I've pulled out a detailed view here, is labeled as a private cannon. Now, this was a problem for weather shooters because farmers who refused to join coordinated networks, these coordinated networks of defense, were regularly branded as wild shooters. And was possibly also a deliberate attempt by the meteorologists to question the weather shooters' desire and self-representation as establishing coordinated and self-contained efficient networks of defense. So let me conclude. Both advocates and opponents of weather shooting agreed that maps held the key to establishing whether or not weather shooting was effective. Comparing the images they created, we are confronted with incommensurable visions of weather. Choices of scale, symbology, and the inclusion or the omission of atmospheric and terrestrial features could make storms appear as socio-natural hybrids that were susceptible to human intervention, or as physical processes that eluded their adversaries physically, but also epistemically. Now, one of the reasons why I believe that these maps are important beyond the history of weather modification is that they offer a historical perspective on contemporary calls for participatory and community-based approaches to environmental data collection. This is an example for how a hegemonic cultural form, such as the map, was appropriated and shifted into the service of vernacular ways of knowing. And these maps also remind us about a wider body of atmospheric maps that exists beyond those produced by physical scientists. In fact, scholars in the humanities have long called for decoupling the study of weather and climate from the numerical paradigms of climate science and to reparticularize and root them in place. And perhaps the weather shooters' maps can encourage us to consider the historicity of weather, to conceive of Earth's atmosphere as a socio-political space that was understood, experienced, and visualized in historically contingent ways, rather than as the timeless, universal, and strictly physical environment that our eyes have been conditioned to see. Thank you.
We're going to start with some Q&A. We'll start with in the room. If anybody has any questions, I'm going to run a mic around. So just raise your hand and I will bring the mic over. RJ, all right.
Howdy, thanks so much. Can you connect this to modern weather shooting today? And what do those maps look like? I'm particularly thinking about how are the Chinese mapping their weather shooting?
Yeah, that's a great question. It's not something that I've looked into, to be fair. So I've stopped with this project. You could continue it further. I stop around 1910, which is when the cannons fall out of favor. But that's a great suggestion. I would have to look at the maps. Thank you.
Was there a proposed method of action for what the shooting was actually supposed to be accomplishing in the clouds, or was it more like, here's an entity that's coming to do us evil, let's shoot at it kind of thing?
Yeah. No, it was more articulate than that. It shifted over time. So at the time that I'm looking at here, initially when the cannons resurfaced around 1896, the main mechanism that was proposed was sound. That was quickly rejected. So there was an idea that sound could in some way cause supercooled water droplets to freeze and act as nuclei for condensation. But that was quickly removed, and then one of the reasons why weather shooting really took off at this time is that because of these large cones that were installed, the cannons produced a vortex ring that was emitted by a cannon. So a lot of the attention then was focused on the vortex ring. That wasn't really a good proposed mechanism. That, I mean, this is a time when there is a particular fascination with invisible energies and a transmission of invisible. So this is also obviously the years of where wireless telegraphy is invented. So we find a lot of that, a lot of also parascientific ideas about invisible energies. There was never one coherent paradigm in which these were explained. But I think sound, the vortex ring, and associated invisible energies were the principal ones. There were some chemical explanations as well, but these were, I think, more marginal. Yeah. Thank you.
Thank you so much for your talk. I came across a similar practice in the Alps in the 18th century, where people were used to shoot in shafts or in ponds to produce rain, and sometimes also storms. Is this something which is related to your practice?
So I've not come across that, but that is very
Okay.
interesting, and it seems like we're talking about the same region, very similar practice. That would be very interesting to look into.
We can share.
Yeah, let's
it
have
was
a-
from Styria and Salzburg. Thank you.
Well, that's also a very big weather. Yeah, thank you.
At the end, you sort of mentioned how some of this might relate to the popularity today of participatory science. You know, like here in the US, we have Purple Air or iNaturalist, and especially as larger government efforts around data collection shut down, there's even increasing funding and interest in these participatory methods. Can you speak to how maybe the relationship of like scale, you know, local, regional scale, and maybe understanding these larger phenomena, what you saw in your research might apply to some of those things today?
Yeah, that's a good question. I mean, I think what seems interesting to me is that what we have here is I feel a genuine example, however ineffective perhaps and misguided in some ways, but it is a genuine example of vernacular, environmental, popular environmental data collection. And in fact, some of this data is I think is interesting and might be used. I'm collaborating with a historical climatologist, and I hope that perhaps some of this data can be recovered and perhaps serve to support some of these models. So I'm not familiar enough with the specific initiatives that you describe, but I think there is a history certainly to be written about participatory environmental data collection. And I feel like efforts like these might be part of that history, and could hopefully inform some contemporary initiatives as well.
Hi. Hello. Hi. Thank you for your talk. Delightful. This is new to me, this genre, so I forgive the ignorance here. So there's clearly a motivation for participatory mapping from the parts of farmers. There's, inherent motivation because of their livelihoods. So, who was funding the publication of the actual products, and were they being redistributed amongst the community, kind of building off of that participatory method? And slightly relatedly, what actual kind of reports or documentations do these arise from? Like, where did you find them? I don't know where they live.
Yeah, thank you. So at this point in time, most of the weather shooters organized activities in consortia. So these were usually by town or by village, sometimes several villages together, and they would pool funds to purchase powder and install the cannons. And I presume this is also. I don't think I have an immediate track of that, but I would assume that this is also where the funds then come out for producing some of these maps, because they're professionally produced. They're professionally produced maps. They were published, and so the weather shooters held regular conferences and events, and they're published. Some of them were published in the proceedings of these. Other were published in local reports. Some of these were found in the correspondence that they shared with each other. But some of these, and then some of the meteorological maps that I showed you were published in meteorological reports funded by the meteorological services, who spend considerable energy and also money to observe these experiments over extended periods of time.
we have any questions from Zoom? Oh, Susan.
Hey, thanks. I really like the way you ended with thinking about like bringing the local back into weather maps. And I'm wondering if you, like what kind of visions you have for what a local weather map, or like how people might incorporate local knowledge into, or like the kind of the subjective knowledge into weather maps that are around today, especially thinking like in the Bay Area, the weather changes so dramatically from one, like you go 15 minutes and it changes dramatically.
Yeah, yeah. Thank you. I mean, there are some great projects that try to embed indigenous and vernacular ways of knowing into. So I think there is a project about I think it's a. I forgot the name. I think it's about mapping Arctic environments, and it was a fairly systematic effort to also talk with local residents and elders in the communities to recover some of that knowledge. I think one way that I think this could potentially be interesting is that so thinking particularly about the kind of cartography that accompanies our visions of climate change is thinking about strategies of adaptation and resilience. Which really require to consider both the atmospheric environment, but also the human environment below, and possibly at scales that are local. So I think that is there's a domain of cartography, I think, that could be potentially there is very interesting work that's already happening, but also interesting work that might happen in the future.
Yeah, this question is from Zoom, from Alec. You mentioned an instance of a locality asking the church to petition a deity to spare their fields. Are there any instances of others practicing like heresy or appealing to dark powers for meteorological intervention? And if so, how did the weather shooters avoid association with such diabolic means?
Yeah, well, that's a good question. So I think in the examples that I've shown you here all stem from the late 19th, early 20th century. There is a slightly metaphysical flavor to some of this, particularly when they are speculating about the vortex ring. We're not far removed from animism and ideas of telepathy, but that is really as metaphysical as it gets. Whereas in the early modern period, this is a much more, it's very difficult to separate the numinous and the immanent in these practices. So there is it's very regular, and in a sense, this is also, of course, deeply related to beliefs in witchcraft and practices associated with fighting witchcraft. It's common to include blessed objects, whether these are blessing the powder itself, including blessed wax, candle wax, including images of saints in these cannons and shooting them up into the clouds. So that clearly points to religious and magical beliefs. There was one case where the entire Gospel of Saint John was fired up in one of the cannons.
All right, I think we can thank Luca.
Thank you.
Thanks for all the great questions.
Thanks so much, Luca. That was like, wow, I never knew anything about weather cannons and have a lot to think about as far as how they might apply to our future and present situation. So thanks so much for that talk. Now I'd like to introduce our second speaker, who is Dr. Dustin Schroeder. The title of his talk, which you'll probably see in a moment, is Mapping the Subsurface Processes of Ice Sheets and Icy Moons with Ice-Penetrating Radar. Dustin Schroeder is an associate professor of geophysics and electrical engineering at Stanford University, so he probably wins the award for longest distance traveled. His research primarily focuses on observing and understanding the role of continental ice sheets and their contribution to the rate of sea level rise. A growing secondary focus of his work is the subsurface exploration of icy moons, and he's a science team member with the REASON instrument on NASA's Europa Clipper mission. Prior to arriving at Stanford, he was a radar systems engineer with NASA's Jet Propulsion Laboratory. He completed his PhD in geophysics at the University of Texas at Austin as part of the UT Institute for Geophysics, and he holds a BS in electrical engineering and a BA in physics, and he had 2 minors. I'm trying to wonder how many years he spent at, it was a bit of time, in Bucknell University in Pennsylvania. So please join me in welcoming Dr. Dusty Schroeder.
You had a wireless mic. No? Okay. Well, that's now it's back. Like shows the notes. I guess it doesn't matter. That's fine. We'll just use this. Cool. Hey, I'm Dusty. So my group's split between geophysics and electrical engineering. We do all ice penetrating radar. So my engineers build radar systems, and they would build radars for things that aren't studying ice sheets, but because they're with me, they don't. And my geophysicists try to understand how ice sheets and icy moons work. And if they weren't with me, they would not only use radar for that, but because they're with me, they do. And then we have people in the middle who sort of analyze ice penetrating radar data. I guess for this audience, the main thing I'm hoping to share with you is to think about the way we map and understand the subsurface of ice sheets, which is mostly with this type of radar. All right, well, that was odd, but all right. I think weather cannons are changing control. Cool. Okay, so I, like any other glaciologist who would talk to you, will start my slides with a plot like this, which is uncertainty and sea level rise over the next 100 years. And this range here is the difference between potentially displacing 4 million people and not. So it's an important question. If we look at the geologic past, our current rate of sea level rise isn't actually that high for what the Earth is capable of doing. And even the steepest slopes here of the sort of most pessimistic, or if you're into sea level rise, I guess optimistic projections are the dashed line. So you see the Earth is capable of more than this in the past. The reason I think that we're not better at this, even though it's so important and impactful, is our remote sensing methods from satellites only look at the surface, right? So you got pictures of the surface, INSAR velocity maps of the surface, altimetry change of the surface, but none of these are imaging the subsurface conditions and processes and properties that are largely governing change. That's why radioglaciology as a discipline exists. I write it with 2 words because it seemed clear to me. It's kind of like radio astronomy, like astronomers use radio waves, but glaciologists use radio waves. But some British dude published a paper in the 80s where it was 1 word, and so everyone but me does it as 1 word, but someday we'll win them over. This data is collected mostly from airplanes, like this DC-3 airplane that fought in the Battle of the Bulge in World War II, and then was bought by the Air Force of the nation of Mali, and then was bought by Canadian bush pilots. And then this antenna was attached under here, so a radar antenna underneath the wing, and then flies along like this cheesy cartoon, sends pulses down and makes these vertical profiles through the ice. So slices of cake or maybe outcrops of rock on the side of the road, but looking through ice. This is the sort of profile that modern data produces. So this is 4 kilometers thick and about 500 kilometers long. You can see mountains underneath. You can see the ocean here, the edge coming up. You can see layers inside it. Again, sort of isochrones like layers of rock or tree rings. This is a map of half a century of every nation that is into this sort of thing, every line they collected. And when you grid it together, it makes a map like this of what the continent would look like without the ice on top. And this is mostly how glaciologists use this data. Maps like this go into the ice sheet models that were used to make the predictions I showed at the beginning. And then physical glaciologists use shapes and layers like this to sort of do like structural glaciology and think about past and current ice flow. My group and others also look at the signal itself. So this will be the main part. I sort of try to build your physical mental model a little bit for the things to come. This is a subglacial lake. So this little flat thing is a lake. This is mountains on the side in ice penetrating radar data. We know it's a lake partially because it's flat, which is true for all lakes you will have encountered for the same reason. But we also know it's a lake because it reflects brightly. So if you like remember maybe like a high school physics class, maybe your teacher like tied a string to the wall and like wiggled it and it like bounced off the wall. And you could like tie the string to another string that's just the same size and it just goes through, and then you can tie it to a medium string and like some goes through and some comes back. And then it's about like how different is the velocity in the strings is how much is reflected back. That's basically all you could be a grad student in my group knowing that. And that produces these differences in dB, right? So dB is like exponential. So you say, okay, there's a range of like 40 dB here. So that's 10 to the fourth. So if you look at all these materials that could be under the ice sheet, they vary by like 10,000 times in their strength. And that's a big old signal. You can be wrong about just like a lot of stuff and still see something that is 10,000 times brighter. Now, the reason this is not a totally trivial undertaking is that the absorption also varies with temperature. So you can see here, dB, so exponential per kilometer. When things are really cold, it's like 1 or 2 dB. That's barely any absorption. And as it gets warm, you get like 50 dB per kilometer, which is giant. And this makes sense. My dad was an appliance repairman, and when I fix appliances with, like microwaves with him, put a cup of water in the microwave, it rotates water molecules with microwaves, boils water, that's how it works. When the ice is frozen, it can't rotate that way. So if you put an ice cube in your microwave, it won't melt, or it won't melt faster than it would on the surface initially. And so that's what's happening here. As you get little bits of water in the ice column, way better at absorbing those energies. And so now you get this challenge of if you see something's bright on the bottom of the ice sheet, is it bright because it's more reflective, or is it bright because it's colder? And if you use signals like that, you can say lots of other things about inside and beneath the ice sheet. So you can say things about the temperature, crystal fabric, whether there's water on the bottom. You can see the ocean coming underneath, fracture, water going through the ice column. Okay, so that's like a mental model in terms of the way of making these measurements. Now I'll talk to you about like some places with names and how it's done. So Amundsen Sea Embayment is a sector of Antarctica where things are changing super quickly. There's Thwaites Glacier, which you may have seen in the news. People like to call it the Doomsday Glacier. I mean, people like reporters, not like scientists. But it is like the most potentially unstable, rapidly changing glacier in Antarctica. It was so clearly that there was this collaboration between the US and the UK that you could only propose to study Thwaites. It had this logo that seems like pro-collapse because it's got this arrow. The teams had these acronyms like Tarzan and Ghost, and like I'm involved with Time, and there's this project that didn't have an acronym. They felt bad about themselves, so now they're called Thor. And so we all went and we all studied. We were supposed to study this glacier for like a couple years, and COVID hit, so it's been like forever that we've all only studied this glacier, which is cool, and I think it's important. But you could imagine there might be other glaciers or contexts beyond just this one. So here's Thwaites, it's flowing this way. Ice flows like a viscous fluid, so you could imagine if I like weirdly piled a mountain of honey here, and then it started to flow under its own weight. That's sort of what ice is doing. You got Thwaites here flowing that way. You got a pine island next to it, which is like the second most mass lossiest, unstabliest glacier in Antarctica, right next door. And then even if you haven't thought about viscous flow before, it's kind of weird that there's like this tumor of ice that sort of turns the corner. It's hard for a fluid to do that. Also weird if you map where water should flow underneath the ice sheet from this region, it flows through Thwaites, whereas here the ice flows through Pine Island, and that glaciers normally don't do that either. So I think the reason we're not better at this is that the data along this boundary was collected at the boundary of 2 surveys. So this brown survey here was a 150 megahertz radar with short and long pulses that were collected, developed and collected by the nation of the United Kingdom. The purple survey was a 60 megahertz chirped radar with high and low gain channels that was developed and collected by the nation of the state of Texas. And everything interesting here is right at the boundary, except for one reflight line. So because I have both engineers and scientists in my group, we did have students who thought mercilessly cross-calibrating that data was interesting and fun and a good use of their time. And over years, we did cross-calibrate it. We made this map of how reflective the base of the ice sheet is. And you know from earlier that these hot colors are warm, wet, thawed bottom of the glacier. And this blue color in this region is where the ice sheet is frozen to the bottom. So we can say, okay, that's why ice is flowing around there. There's this piece frozen to the bottom. Now, that might not seem like a good way to set the boundary between 2 rapidly changing glaciers, and it might not seem terribly permanent, and I would agree with you on that. So you could say, okay, maybe that's not what's happening there. So another thing you could say, maybe the boundary's there because of these shear margins. That's where ice flows like fast next to where it's flowing slowly. These black lines are shear margins on topography, and you say, oh yeah, that makes sense. Here's a volcano. Turns around there, mountain, black line, mountain, all makes sense. Except this boundary, it's going from like low topography to high, cutting across these highlands. Like I would never draw the boundary there. So this is so strange that this was actually the whole time project we're involved with. We had students camping in Antarctica for months to try and measure and ask why that shear margin is where it is. One hypothesis is that frictional heating is warming the margin, and that's why it is where it is. In order to make that measurement, radar systems, no radar systems that currently existed would work. Could have tens of kilometers offsets. So our group developed a software-defined radio and fiber optic-based system that could make that measurement. My student Danny, lying on the ground there, is writing that paper up now. But even if he's right, like even if he finds that it is warm ice, like that's still kind of temporary. Like it's just warm ice in the margin. That doesn't seem like a permanent boundary. So then maybe you say, okay, maybe it's further downstream. So here we are, Pine Island Thwaites, the ocean, everything that's red here is lowering and accelerating, and the blue bit is slowing down. So you say, okay, maybe this is why the boundary is there. And that's what's happening there is the ice is going afloat, it's hitting some high topography on the bottom of the ocean, and it's holding back the ice. So okay, maybe that's it, that sets the boundary. Everything is upstream of that. Now in my field, this counts as data richness, which is 1 line from 1979 and 2 from 2009. And actually it's amazing because this 1979 line is the only line in this entire quadrant of Antarctica. And it's right there over that ice shelf. That data was recorded on 35 millimeter optical film, stored in 1,000 canisters in the archives of the Scott Polar Research Institute at the University of Cambridge. And so in order to analyze this data, I bought with my new faculty startup this scanner that was meant for digitizing old Hollywood movies. I had 2 friends who had studied art history who were somehow unemployed, and they came with me and we scanned 2 million images of all this film. And you can see we had these images here, like here's the original publication, here's our scan, you can see the lake, you can see this piece of 50-year-old masking tape that was like nature paper, boom, right there. And once we did all of that, you see a couple things. One, I'd have been really proud if I was a radar engineer in the 60s who made this vacuum tube-based film recording. It's a good-looking radargram. You can see here where the ice shelf gets thin, goes afloat, or grounds and then goes afloat again, and you can see that's getting smaller. You can also see that the melt going through isn't happening uniformly, which is what you would see from space, but you can see these crevasses melting through. And this suggests this thing's going to collapse in the next couple of years. We've sent, not us, but we, glaciology, have sent a robot under there, and they saw the same crevasses, which is good, feeling like we're not liars. But yeah, so anyway, ice shelf's not going to stop it. Separately, and because like this, I make this joke in so many talks, but maybe this is the audience where someone will do it. All of this film is available to you as a hobbyist on Radar Film Studio. And you can be at a party this weekend and just take it out and start looking at tiny digits of film and helping us read and correct the positioning and all this out. You'll be so popular. But yeah, this is how we're getting this film. We've done the same at the Technical University of Denmark with Greenland data. Total treasure trove of data. Okay, quickly over with the time we have left. I also do planetary radioglaciology. I'm on the Europa Clipper mission, which has ice penetrating radar called Reason. European mission also to the icy moons with radar called RIME. We did do that on purpose. The Europeans almost named this thing Jimper, which would have been way less catchy. But yeah, we've got it. We got 2 ice penetrating radars going. On this front, everything I've told you so far is mostly radars that have like 10 kilowatt powerful transmitters flying like 500 meters over the surface. This is like a 10-watt transmitter flying hundreds of kilometers above the surface. And so that's a much more challenging situation. But you know from that earlier slide, the colder ice is, the easier it is to see through, and space is very cold. So that's why we think it will work. One of the things we're trying to answer is the ice shell of Europa thin or thick? This has implications for the habitability of the moon. It has 2 frequencies, mostly because there's two things to be scared of. If you're more scared of surface roughness, you want to go low in frequency to have a really long wavelength so the roughness doesn't seem that long compared to your wavelength. But like diabolically, Io, this other moon of Jupiter, has the volcanoes that eject these particles that interact with the magnetic field of Jupiter that produce super loud radio noise at all frequencies under 40 megahertz. So it just blasts everything you'd want to use for this. So the Europeans chose just to do this anyway and like hide behind the moon so they wouldn't get this noise. And then we sent one of each so that always, hopefully, one of them works. The other thing I'll say is you may be tempted to ask what is the penetration depth of this radar? And that's just like not an appropriate question, because I think a lot of people think they're like buying a camera from like Best Buy, or if that exists, or Amazon, and they're just gonna have some number. And so you'd say, okay, Dusty, cool. We're gonna pretend we have 100 dB of attenuation to work with. Here's a model of attenuation in the moon. And be like, all right, when do you see the ocean? We're going down, oh, I don't know, 15 kilometers, 20 kilometers, that's your penetration depth. And then you would say, what if it was thicker? What if it was like 30 kilometers? You go, well, 30 kilometers, I don't know, 29. And so the answer of what is the penetration depth, which NASA is not into having in their spreadsheets, is most of the way. Because, you know, you're gonna see, because like the top is cold and the bottom is the ocean is warm and wet. So you're gonna make it through the cold stuff. So the real answer is most of the way. So you can also bust that out at a party when someone casually asks about the penetration depth of an ice penetrating radar. If you're not persuaded by that, if you're like, that was cute, but like, I still don't think you're gonna see the ocean, and how are we gonna find aliens? Then, okay, there are papers, there are recent papers that suggest there's water in the ice shell, in the shallow, cold part of the ice shell. So we think chaos regions may have been formed by lakes. We think impact plumes, warm, cause temporary melt there. We think there are processes that formed on ridges that cause refreezing, injecting water up, refreezing again, and injecting water on either side. And so the hope is when we get there and fly over chaos region, it looks a lot like this, which is an iceberg on Earth. My group is also engineers. So we are trying to think about how we'll collect observations in the future. One of my most recent PhD graduate developed a system that you could fly in a drone. He was also a Stanford undergrad, which you can tell by the super clean branding of this slide. But you throw this drone, it automatically flies 25 kilometers, collects data, lands, you change the flight plan, you change the battery. We actually developed this during COVID. I got a permit to fly over Lake Log here on campus, which is way harder than getting a permit to fly in Antarctica or Greenland or Iceland. But this is working great, and we're working with a group at Scripps to make a much larger version that is gas-powered and can fly 400 kilometers, and you could really imagine replacing the DC-3s. What's exciting about this is you can use these reflights in the layers in the ice to do the same sort of interferometric analysis you do for the surface to get 3D ice flow. Stands to be super transformative in the field. And then again, if you're still bored this weekend, you can go onto Orca Radioglaciology and buy a software-defined radio and make your entire own ice-penetrating radar and drone and operate it. And I just recently was sent a proposal to review by some foreign research group which was proposing to just adapt and use our system to build a new radar. So you too can build ice-penetrating radars. I think that's it.
Thanks, Dusty. We have 10 minutes for questions. Juna.
That was a great presentation. Thank you. I had a question though about albedo, and so I definitely feel like your point about the three-dimensionality and about the the limiting factors that aren't obvious from the surface are really important. But from the simple astrophysicist perspective, when you change the albedo of a planet, like you get into a runaway and you don't get back. And so I guess I'm just curious what the state of the art is there in terms of the ice sheets and the melting, and whether that is kind of bouncing around our classical albedo, or actually are we getting darker?
So albedo feedback is super important for sea ice. That's most of the show with sea ice. And you could even convince yourself in Greenland, where you get surface melt, that albedo is important, though I still don't think it's a first order effect. Antarctica is a much more complicated question. So in places like Thwaites, where Antarctica is really melting rapidly, it's melting because it's being melted by warm ocean water. That warm ocean water has been warm for millions of years. We're not warming it. The way it works in Antarctica is you have cold water on the surface, and then this warm water just doing loops around the continent. Atmospheric changes currents. Those currents change the warm water. The warm water goes up and hits the bottom of the ice sheet. But that is a much more complicated system with much more nuance in it. So not only is it not an albedo-driven effect, it's not even a directly atmosphere warming-driven effect.
I wasn't suggesting the effect was albedo driven. I was just asking about the change in the albedo and what is the status of that. I fully appreciate the mechanism that's melting the ice there.
Yeah, I mean, it's pretty small. In Greenland, you get surface melt where the melt itself absorbs energy, but then those lakes drain to the bottom and it's white again. So the big ice sheets are not albedo changing objects in a significant way. I'm sure some snow person would disagree with me, but from like a sea level point of view, not a significance.
So I'm not sure I followed the conclusion of the Thwaites Glacier, the new radar information. Is it sliding more than we thought or less, and what's next?
So I think the question is with Thwaites. Thwaites is changing from the ocean. The question of all these things along the boundary is, what sets the boundary between these two glaciers? And it can one just grab the other, right? And when you think about an ice sheet model progressing in that way, that really changes how far it propagates inland. So it's not so much about how it's changing now, but as it retreats, how do we imagine that retreat, and how much ice and sea level can it really grab is extremely different. I would say we're going through sort of the scientific method and falsifying things. And I would say every mechanism we look at to describe why that boundary is where it's there does not seem to be why. So that would suggest that it's a pretty ephemeral boundary that probably is pretty up for grabs for other glaciers to grab pieces of it, or for more likely Thwaites to grab that sort of tumor from Pine Island and add it to its potential sea level change. But that's sort of post or as we retreat.
So it still wasn't clear. Is more water or less?
I think it depends on your time scale. I think it depends on your opinion of how fast you think Thwaites gets unhooked from its current grounding zone. Probably means Thwaites has more water available to it. But you could equally say, okay, well, that's taking stuff away from Pine Island, and if you find Pine Island's changing faster. So the net sign, I think, is not obvious. I guess maybe another way to think about these process questions, because it's really different than surface or even atmospheric things where we sort of know the physics of changing. So an example I give in public talks is like if I insanely went outside and like hung from the roof by my hand, and you were like, is Dusty gonna fall from this building today? Everyone's like, yeah, definitely. But if you're like, is he gonna fall in the next 5 minutes or minute or 2 minutes? Somebody might be like, oh, it's all about Pinky sweat. His Pinky seems super sweaty, gonna fall, definitely. Someone else could be like, oh, you forgot about wrist fat. He's kind of got like a fat wrist, and in a wrist fat dominated regime, Pinky sweat is irrelevant. And like, these are all things that, because we asked this insane question of like, are you gonna fall like right now? And that's what it's like with the glaciers. Like, we're asking for human timescales that are fast. And so we're arguing with each other about like which process is going to dominate on those scales. And I think where we are and what makes this a cool period of discovery, different than other parts of climate science, is we're making first order process discoveries. And I would say Thwaites right now, we're like ruling things out in terms of its boundary. Its change is driven by the ocean, no questions there. But in terms of its boundary, still unclear.
Maybe, are there any questions in Zoom? No questions in Zoom. All right. Thank you, Dusty.
Great. Thank you.